So the other day I was playing around with looking at the mathematical operations, the arithmetic operations. Which, yeah, you're probably familiar with my position that they're not all operations, and the ones that are noted aren't noted in the right way anyway, because the one that comes after exponentiation is tetration, which means fourth, but you might notice there's already more than 4 layers here if you do it right. Anyway, so we start with existentials, 0 and or nothing, 0, and unit something. It's not really 1, it's not a number yet. It doesn't exist as a number yet. And then you get into incrementation, which gives you incrementation and decrementation. And so what I was doing is I was looking at the in and out. And I actually started with addition and subtraction, because here it's relatively trivial. These guys were not, it's not doing really all that much, but so much of modern mathematics revolves around addition and multiplication being like considered these like base operations for shit. And so it's like, well, okay, how far can we go before that stops making sense? Turns out, not very far. So when you look at addition, right? So you take addition as your base operation, right? A plus B is C, right? So you've got these two guys over here and another guy over here. So you have inputs of A and B and an output of C. But we can reverse those, right? So keeping the same numbers. So say it's like 2 plus 3 is 5, right? So C is 5, B is 3, A is 2. And I'm just going to hold that constant when we look at subtraction, right? So 5 minus 2 is 3, and 5 minus 3 is 2, right? So if I put in A and C, I get out B. If I put in B and C, I get out A. All right, so we get this nice progression from C, B, A over here, A, B, C, C, B, right? We see this pattern here. We end up with the same pattern occurring with multiplication and division, right? We've got 1 plus with addition, 2 minuses with subtraction, 1 times with multiplication, 2 divisions with division, right? So A times B is C, C on A is B, C on B is A. These look very similar to each other. They act very much like each other. Formally, basically everything that's happening here, they look the same. The way that everything we're considering, the way that we're looking at it right here, right now. Now, when we go over to exponentiation, the hell just happened? When we go over to exponentiation, the story changes. All right, we take exponentiation to be the base operation. So we get A to the B is C, input A and B, output C. Now, this version of it here should be our first inverse, where we put in A and C and we get out B, and that is logarithms. So this is, I'm trying to notate it, log base A of C. It's very hard to notate when you can't do subscripts and shit, but anyway, just plain text, log base A of C is B, right? So put in A and C, we get out B. But then there's another inverse, allegedly, of exponents, which is the roots. But if you look at that, it's really another exponent. C to the 1 on B gives you A, right? So you can put in B and C and you get out A. So here the one that's unique isn't the one that we're calling the base operation, like it was with multiplication and addition. What we're calling the base operation is paired with something else. So if exponentiation is the base operation, then division should be the base operation, and subtraction should be the base operation. I think there's actually a fair argument to be made for that, personally. But there's definitely an asymmetry occurring here, right? So here, generally addition, multiplication, and exponentiation are considered to be the primary operations of their respective levels. However, if the primary operation is the unique one, which it seems that addition and multiplication are setting the stage for, as with addition and multiplication, then exponentiation is not the primary operation at this level. Logarithms are. restructuring things, we arrive at the following, right? So now if we look at it this way, where logarithm is our base operation, we get log base a of b is c, so we input a and b and we get out c. And then we get two versions of the exponent, where we get a to the 1 times c is b, and b to the 1 on c is a. And there's a small difference here, but either way it's an exponent, right? Whether you're taking a power or a root, either way, it's an exponent, right? Now, you might notice that the way these are written is very different from addition and subtraction, right? Or addition, subtraction, multiplication, and division, these guys, right? These are all written in a form that's pretty much identical. The only thing that's changing is that operator, which, as I've noted before, isn't really an operator. But anyway, in here, this looks radically different. So how about we do this? We'll just establish something here for the sake of our consideration here. I don't give a shit if anybody ever uses it outside of this. Don't care. We're just showing the point here. Exponents should be written differently so that the exponent comes before the base, as in C. And here I'm going to use P and Q because they are just mirror images of each other, and we've got this this inverse thing that's happening in the two exponent forms. So P and Q are going to be nice for this because they just visually indicate that mirroring, but otherwise they're the same. It's a circle with a line, a tail that extends down below. So CPA is B. So this would be A to the C is B, the way that you would normally write that, right? So the power of C is on the base A. All right, so we input A, C, and get out B. And then the inverse of that is Q. CQB is A. So we input B and C and we get out A. Ideally, logarithms should also be written in this same sort of format, right? So here I'll just use a big capital L for that. So A, LB. Now what this means is A is the base of the logarithm, B is the exponent, or the power, and C, or wait. No. B is the result of the exponent and C is the power. Right. So we input A and B and we get out C. Right. Altogether at this point we have the following. So addition looks like this. So for example, if A is 2 and B is 3, then C is 5, and that's true across the board for all of these guys. Now with multiplication and division we get this, and it looks very much the same. It has the same basic format. And then there's just a few caveats, right? And if A is 2 and B is 3, then C is 6, right? So the main caveat here is that C on 0 is undefinable, so you can't have A or B be 0 and get all of everything to work out. All right. Now we have logarithms looking the same way, okay? And in this case, if A is 2 and B is 3, then C is approximately 1.58496250. I think the next one is like 0.7 whatever, but I'm just going to do a U there in my standard notation for repeating, or, well, for non-terminating, non-repeating expansions. And now there's multiple caveats, right? So for AL0, for A is not 0, and for 0LB, for B is not 0 and B is not 1, so B could be 0 or 1, and that would work. And over here, A could be 0, and that would work. And for 1LB and for 0QB, these are all undefinable. There's probably other caveats, but those are the ones that I noticed while I was working this up, right? So, and now notably, so this is this form right here. 0L1 would be 0, and 0L0 would be anything greater than 0, and this is, of course, not taking into account complex numbers and all kinds of other shit like that. But considering the reals, that's where you end up with this. And now you end up with these guys looking the same. But logarithms are now analogous to addition and multiplication instead of exponents being addition, or analogous to addition and multiplication, which is an interesting result. I didn't expect that when I was looking at this. I just made up a table and I was like, okay, where is this taking me? Because I knew this was going to be a mess. I knew this was a mess. And I did also know in the back of my head that roots and exponents are actually the same basic thing as each other. So very quickly I noticed, wait, logarithms are the actual distinct thing here. So logarithms are far more analogous to addition and multiplication than they are to subtraction and division. But classically, we view logarithms as being derived from exponents. I even saw a video of somebody opening with that claim that logarithms are derived from exponents. Historically, they're actually not. They were noticed in a completely different way for a completely different reason. And then somebody put it together that, oh, wait, this is what these are. And we should have seen these a long time ago because we've been doing exponents for thousands of years. It should have occurred to somebody that you can just undo it. But it never did. So, until quite recently, I think it was the 17th century, 1614, I think, was something like that was when people started putting together tables and stuff. Anyway, yeah. So I found that interesting. Don't quite know what to make of it, but I found that interesting.